So this is a set of coupled differential equations in terms of two variables, transverse displacement v and section rotations theta. And in the case of thin slender beams, when section rotations are synonymous with are identical with the slope of the deflected shape, then this set of coupled differential equations reduces to a single fourth order differential equation that you know so well. So we can try to solve this and try to identify what are the primary variables and secondary variables by starting with the weighted residual statement, and we do that by considering the approximation. Transverse displacement is approximated as v hat and section rotations are approximated as theta hat. So the domain residual is now a vector given by these two terms. So two-dimensional vector. So we have we should bring this into inside the derivative. So this is the domain residual, and if we establish the weighted residual statement, so what will be the weighted residual statement? It's a equation, it's a vector. Now your domain residual is a vector. So what should be the weighted residual statement look like? It will be a domain integral multiplied by a diagonal matrix R omega 1, or let's say R1 omega and R2 omega d omega. So this term is what I am referring to as R1 omega. This second term is what I am referring to as R2 omega. So very natural. I mean, when you have a vector, obviously it can only be pre-multiplied by a matrix to generate a square matrix to give another vector, and that is what you do. The statement of weighted residual statement is arrived at by multiplying the weighting coefficient, weighting function. Now the weighting function is not a single function, it will be a set of two weighting functions and arranged in a diagonal format, I mean the diagonal matrix. So one weighting function for one row and second weighting function for second row of this statement of weighted residual. And similarly, if there are more number of equations, you can have as many more weighting functions in the matrix of weighting functions. So collectively, I can write this as matrix of weighting function, vector of domain residuals integrated over the domain is equal to 0. That's the weighted residual statement. And now I can evaluate, this is also vector, null vector. So together, if I look at it, so it boils down to what we are familiar with, single equation at one time, integrated over domain, integrated over domain. Right, so you are familiar with this statement. One equation, weighting function multiplied by this statement, residual term, integrated over the domain, and we follow by standard rule. Apply integration by parts, take the derivatives from residual term to the weighting function term, and look at the boundary term. And similarly, the second term will perform the similar operations. So let's look at this, how this looks like. So the first function is, let's say 0 to L, the domain, W1, and the residual is the vertical, the moment and shear relationship. Minus kGa dV by dx. And the second equation, let's just write the second equation also. W2 multiplied by TDX kGa dV hat by dx minus theta hat minus q. I guess that is all. Yep. Minus q. So that's the second equation. So let's work out the first equation. First term, integrate this by parts, integration of W1 multiplied by this expression. So first function multiplied by integral of second function, zero to L, minus integral of differential of first function integral of second function. Right? And this one remains as it is. W1 multiplied by kGa dV hat right. So this is equal to 0. So this leads to the identification. This is the boundary term. So this is secondary variable. What is the secondary variable? This is moment. This is curvature. Rate of change of sectional rotation is the curvature multiplied by flexural rigidity. So this is the bending moment, right? And corresponding to that is the weighting function term, and weighting function term, which weighting function, which this has to be substituted by the variable of the differential equation, corresponding variable of the differential equation. So this term product should always be a work quantity. So which will be the corresponding work quantity, corresponding, either we have a choice between V and theta. So the work quantity can be achieved when we couple with bending moment. So this has to be, and of course this is the primary variable of this term as well. Primary variable, that is section rotation. Right? So this identifies the primary variable, that is section rotation. One primary variable is the section rotation. And what is the highest order? Highest order of derivative in the weak form. We are developing the weak form. Of weighted residual statement. Weak form of weighted residual statement. What is the highest order of derivative? All terms, they have differentials of the first order, dw by dx, d theta by dx, dv by dx, right? So the highest order of derivative on the primary variable, that is theta, I mean everywhere else, all other terms. So the highest order of derivative in the weak formulation of weighted residual statement is 1, and therefore linear interpolation, first order derivative should exist. Should exist for this approximation to hold, to get something in the equation to solve for. So the first order derivative should exist, should not vanish, and therefore linear interpolation, this simplest interpolation model which will satisfy this requirement of non-vanishing condition on the first order derivative, is linear interpolation. For theta should suffice, right? So linear interpolation for theta, very easy. We can have it's a beam, so we define by two endpoints. So we have primary variable at two endpoints, and we can fit a linear polynomial between two primary values of the primary variable at the nodes, two nodes, end nodes, right? So linear interpolation, very well. We already know this linear interpolation very well in our earlier discussion. So C0 continuity. So C0 continuity, because primary variable is the zeroth order derivative of theta. So this is C0 continuity on theta. So C0 continuity of theta is implied. Now let's look at the second row. Second row of the weighted residual statement. Again, we carry out the developing the weak form. So 0 is equal to first function w2 multiplied by kga dv hat by dx minus theta hat, and this evaluated at x is equal to 0 to L minus integral 0 to L dw2 by dx multiplied by kga dv at dx minus theta x dx minus integral 0 to L w2 q dx. So that is the weak form.